Hello, everyone. This is Jan, and we are continuing with our discussion on inorganic chemistry advanced level. Currently, or previously, we looked at periodic properties, and we have covered so far most of them, looking at atomic radius, looking at electronegativity, looking at ionization energy, looking at electropositivity, electron affinity, melting point, and so on. Now let us trace back and we look, or let us take our attention to the solubility of ionic salts. How are these salts, the ionic ones, how possible or how fast or how are they made able, or why do they have to dissolve in water? Their solubility of these ionic salts in water is being governed by two energy terms, and that is why we are going to encounter lattice energy and hydration or solvation energy. Now, the solubility of these ionic salts, they are governed by two terms, that is lattice energy and hydration energy. And what is lattice energy? We can define it in two ways. One is the amount of energy that is required to break 1 mole of an ionic salt into its constituent gaseous ions at standard conditions. We are looking at an ionic salt being broken down into its constituent gaseous ions, and this one takes place at standard conditions. You look at the equation below, where we are having sodium chloride salt and having lattice energy change in heat, the H is equal to lattice energy, and we are having the ionic salt, which is sodium chloride, breaking down. 1 mole of this salt is being broken down into sodium ions and chloride ions in their gaseous states. Now, another way we can define lattice energy, we can define it as the amount of energy released when 1 mole of an ionic salt is formed from its constituent gaseous ions at standard conditions. Now, here we are forming the ionic salt. Here, the ionic salt is getting formed from its constituent gaseous ions at standard conditions. That is sodium ion from the gaseous state plus chloride ion in the gaseous state. It gives us sodium chloride in the solid state. And the H is lattice energy. Now, we are having a difference. The other side is the amount of energy needed to break down. That means when we are breaking down 1 mole of an ionic salt into its constituent gaseous ions, that is a purely endothermic reaction. That means we need, or there is an energy that is needed. There is energy absorption. It is endothermic. You expect change in H, dH, to be positive. But if you are forming an ionic salt from its constituent gaseous ions, then you expect the change in energy to be negative, because here the amount of energy is going to be released, so it is exothermic. Now, you will have to encounter lattice energy challenges when you are in Born-Haber cycles or the energy level diagrams. Whether they have given you lattice energy in negative or positive, look at a change that is going to take place. If it is bond breaking, it must be positive. So that means in your calculation, when you are given the lattice energy in negative and you are having bond breaking, you have to change it and use the positive. If you are given it, or if you are given lattice energy as a negative or as a positive, and you are having bond formation, that is forming a salt from its constituent gaseous ions, then you must use a negative, because you must release a particular amount of energy. Now, this guy, the ionic salt, has already been dissociated into its constituent gaseous ions. Then you expect the concept of hydration energy, which is the amount of energy released when 1 mole of gaseous ions is fully dissolved in water at a given temperature. Now, what happens when you get 1 mole of these gaseous ions and they are fully dissolved? You put them in water and water fully surrounds these ions. The forces of attraction between the water molecules and these ions, the charges in water and the charges in these ions, attract that water closely around these gaseous ions. Then you call it hydration energy. It is negative amount of energy released when 1 mole of gaseous ions is fully dissolved in water at standard or at a given temperature. Now, hydration energy has a negative sign because it will involve the attraction between a charge and water molecule, which releases energy. There is an attraction between the charge on that gaseous ion and the water molecule, which will release the energy. So these forces of attraction are the ones that result into releasing energy. And B, each of the ions has its own hydration energy. For example, you look at the magnesium gaseous ion plus aqueous, that is addition of water, you get magnesium 2 plus aqueous. Hydration energy at 298 Kelvin is negative 696 kilojoules per mole. For sodium, it is negative 0.406. Chloride, it is negative 377. Now, therefore, the hydration energy for complete dissolution of sodium chloride, you add the hydration energy of the respective gaseous ions that make up this ionic salt. Now, don't make a mistake. First, write an equation that gives you these ions dissociating fully. Then you will know the ions, the number of ions. For example, in this magnesium chloride, write an equation of magnesium chloride salt, a salt in solid state. Then let it dissociate into the constituent gaseous ions, that is magnesium 2 plus and chloride minus, but there are 2 moles of the chloride. So when you are calculating the hydration energy, you are expected to get 2 times negative 377. Now, for us, or to get the hydration energy, we look at the size of the ionic, or we look at the ionic radius of the cation. Now, we are saying that the smaller the ionic radius, the higher the charge density, and so the greater or more negative the hydration energy. Now, if this guy is small, for example, look at magnesium and sodium. We are having a trend in atomic radius. Across the period, atomic radius decreases. Now, look, as you are moving from group 1 to group 2 within the periodic table, more electrons are removed that are present in the outermost quantum shell. So what will happen? You expect to have the same electron number, but the proton number is high in magnesium than sodium. So there is a great effective nuclear charge. So expect this guy to have a small ionic radius. If it has a small ionic radius, then, and the charge is high, what is charge density? You get the charge on the ion divided by the ionic radius. So the smaller the ionic radius and the higher the charge, then the greater the charge density. And once the charge density is high, then you expect these guys, the water molecules, to be strongly or closely attracted. Hence, there is high hydration energy. Water is a suitable solvent for dissolving ionic salts. Why? It is a polar solvent and it has a high dielectric constant. It has a large dipole moment, so that ion dipole interaction is high. It has a large dipole moment, so the ion dipole interaction is high between the water molecules and other ions. That interaction is very strong. If the solvation energy of a substance is greater than its lattice energy, then you expect the substance to dissolve exothermically in the solvent. That is, look at the lattice energy having a positive value, and then look at the hydration energy having a negative value. And once the hydration energy or the solvation energy is very great and negative, then it will, or the positive lattice energy won't counter-interact the negative hydration energy. So you'll expect the substance to dissolve exothermically in the solvent. If the solvation energy is less than the lattice energy, then the substance dissolves endothermically. However, if lattice energy is much larger than hydration energy, then the salt does not dissolve, because we need to have a change or the enthalpy of the solution to be not very much positive. If it is too much positive, then that means that salt is not or does not dissolve in water. Because we are calling the enthalpy of solution the heat change that occurs when 1 mole of ionic salt is fully dissolved in water at a given pressure. There is a heat change that will occur if this guy, the ionic salt, is fully dissolved in water. So now that means if the lattice energy is much larger than hydration energy, there is a great amount of energy that is required to split this ionic salt into its constituent gaseous ions. So what will happen is you will expect this guy not to dissolve because the hydration energy is very small. So this one takes us to the Born-Haber cycles, where you have sodium chloride salt plus aqueous. It gives you sodium plus aqueous plus chloride aqueous. Down, this guy, or when you get this sodium chloride, then it dissociates into, by lattice energy, it gives us the sodium plus gaseous, chloride plus gaseous. And then these gaseous ions, they are the ones that dissolve in water and give us the salt, or when these guys are fully dissolved in water. So that one shows the Born-Haber cycle. You can check on the net to get a more good Born-Haber cycle, better than that, because this one is having some arrows and not directly showing where they should be. But from that, we have a conclusion that enthalpy change of the solution is equal to change in lattice energy plus change in hydration energy. And whenever we use this formula, whenever this formula is applied, then the value of lattice energy must be positive. It is because the formula is only valid when the salt is becoming decomposed as shown in the cycle above. But if this salt is being formed, then we cannot use such a formula showing that enthalpy change of the solution is equal to lattice energy plus hydration energy. We have some sample questions. The lattice and hydration energies of magnesium chloride are as follows. You are required to draw an energy diagram or Born-Haber cycle for the solubility of magnesium chloride and indicate the energy changes that occur. Then you are required to calculate the enthalpy of the solution of the salt, that is magnesium chloride. You have question 2. where you're having potassium iodide, you are required to draw an energy level diagram, and then or a Born-Haber cycle to show the energy changes during solubility of an ionic salt in water. Then you are required to calculate the hydration energy for potassium iodide when you are given the enthalpy of solution and lattice energy. What are those factors that affect lattice energy? We have ionic charge, that is the charge on the ion, e.g., you're having the sodium ion, you're having the magnesium ion, you have ionic radius, that is the distance between the ions, you have crystal structure of a compound, and maybe some of a few explanations about it is that lattice energy is directly proportional to ionic charge. The higher the ionic charge, the greater the lattice energy, and the lower the ionic charge, then the lower the lattice energy. Why? If the ionic charge is large, then you expect the electrostatic forces of attraction between the opposite charges to be stronger, leading to high lattice energy. It will require you, because you expect the electrostatic forces of attraction between the opposite charges, between these guys, the cation and the anion, between these gaseous constituents that form this ionic salt, to be very strong. So that means this guy will require a large amount of energy for it to be broken down into its constituent gaseous ions. And if the ionic charge is small, then you expect the electrostatic forces of attraction between the opposite charges to be very weak, because the bond that is formed is not as strong as when the electrostatic forces of attraction between the opposite charges are strong. So as a result, you will require less amount of energy to break this bond. So you will have a low lattice energy. And it is inversely proportional to ionic radius. That is, if the ionic radius is large, then you expect to have weak electrostatic forces of attraction between the opposite charges, which require a low lattice energy. This is because if the ionic radius is large, then you expect the bonding electrons to be far away pushed from the nucleus. So the strong, or the forces of attraction, or what we call the effective nuclear charge, is very small. There won't be a strong bond, there won't be a strong attraction for these bonding electrons towards the nucleus. And if the distance between the ions is small, then you expect to have the electrostatic forces of attraction between the opposite charges being greater, which lead to a high lattice energy. How is this guy varying? That is lattice energy and hydration energy. Why? What is the variation within the group and within a period? So in A, we are saying that both lattice energy and hydration energy increase across the period. Why are they both increasing across the period? Across the period, we are having the radius of ions becoming increasingly smaller, and as such, you expect the charge density to increase. So as you move from one group of the periodic table to another group of the periodic table, what happens is the radius of the ions becomes increasingly smaller. That is, you're having a decrease in ionic radius, because you expect to have the bonding electrons added to the same energy level, the same share, and as a result, what will happen is that this guy, you will have an increase in nuclear charge, but the increase in screening effect is very small or almost constant. So what happens is the effective nuclear charge is very high. So you'll expect to have a small ionic radius coming in. Now what happens? It implies that this guy can be easily hydrated. If it is very small or possessing a small ionic radius, then you expect also the electrostatic forces of attraction between the ion and the dipole moments of water to be very strong. So you will expect to have this ion being easily hydrated. In B, we are saying that both lattice energy and hydration energies decrease on descending the group. That is, as you are moving from one element to another element in the same group. For example, look at group 1. As you move from the first element, lithium, you go down to sodium, and from sodium, you got potassium. Down to the group, you will have both these guys decreasing. Why? Down the group, you expect the radius of the ions to become increasingly larger, and as such, you expect to have a decrease in charge density, and the ion is less hydrated. If the charge density is low, because down to the group, you are increasing the atomic or the ionic radius. As you're increasing the ionic radius, remember you are in the same group, so all these guys possess the same charge. Now, these guys possessing the same charge, it means that when you carry out or when you calculate the charge density as the ionic radius increases, then you will have the charge density decreasing down the group because it is charge divided by ionic radius. So you'll expect this guy to have or to be less hydrated. And of course, because the radius of the ions is very large, then you will also expect them to exert weaker electrostatic forces of attraction. That is how these guys are varying within the group and across the periods. Now, there is another periodic property that we might talk about or that we are required to talk about. This one gives us a relationship. We have a relationship that we call diagonal relationship. When you go to the periodic table, you look at the elements that are occupying the diagonal positions in position number 1 and in position number 2. Look at lithium in group 1 and look at magnesium in group 2. These guys are in their diagonal, they are in diagonal positions. And we are saying that this relationship within the periodic table is by which certain elements in the second period have a close chemical similarity to their diagonal neighbors in the next group of the third period. So we are looking at elements in period 2 and elements in period 3 that occupy diagonal positions having a close chemical similarity among them. Look, in group 1, we have the first element being lithium, and we have the second element in group 2 being magnesium. So there is a close chemical similarity between these two guys, lithium and magnesium. And when we are looking at the chemistry of different groups, you find out that most of these elements, such as lithium and beryllium, they have chemical properties that are very different from the chemical properties of the other elements in the group. And their chemical properties resemble those chemical properties of the elements in the next group. For example, you look at lithium and magnesium, look at beryllium and aluminium, and then you will have boron and silicon. Let's look at their properties. Why are these guys having, or why do we say they are in a diagonal relationship? This is because these guys possess similar electronegativities. They have similar atomic and ionic radius. They also possess similar hydration energies. We have the similar electrode potentials. and similar charge densities plus similar polarization powers. So the charge density defines for us the polarizing power, the force of attraction that this element will have on the other bonding element. Look at electronegativity, the tendency of an element to attract the bonding electrons towards itself from another element. You also look at the similar electropositivities. That is it, that their tendencies to lose the outermost electrons, the electrons that are occupying the outermost quantum shells. That is electropositivities. We are relating the electropositivity with metallic character. So if an element has a high electropositivity, then that element is strongly metallic. Look, when you go to the periodic table in a group, as you go down the group, then you will have similar electropositivities as you move down the group. But then as you have electropositivity increasing, that means metallic character increases down the group. But as you move from one element to another element in the same period, then you are tending to non-metallic character. That is group 1, 2, 3. They are strongly metals. But when you go to group 4, you will find metals, non-metals, and metalloids. Those ones that possess both metallic and non-metallic characters. Then 5, 6, 7. These are non-metals. And then you have the rare gases, or these guys that are always fully filled, their outermost quantum shells, and they are stable, occupying group 8. So we are looking at the resemblance between lithium and magnesium. And we are saying that these guys both react directly with nitrogen to form nitrides on heating. So when you get lithium plus nitrogen and you heat, you get lithium nitride. And likewise, magnesium reacts with nitrogen to form magnesium nitride. Both of these guys react with oxygen to form normal oxides, that is lithium dioxide and magnesium oxide. Both their nitrates decompose on heating to form a normal oxide, nitrogen dioxide, and oxygen gas. When you get lithium nitrate, you heat, then it will decompose to give a normal oxide, a nitrogen dioxide, and oxygen gas. Likewise, for magnesium nitrate, you will form a normal oxide of magnesium oxide, then you will form nitrogen dioxide and oxygen gas. Both form carbonates that also decompose on heating. That is lithium and magnesium carbonate. They decompose to give us lithium oxide and magnesium oxide plus carbon dioxide gas. Both react with carbon when heated to form an ionic carbide. That is, you get lithium, you heat it with carbon, a salt, then you form lithium carbide and magnesium dicarbide. Magnesium carbide. Both form chlorides and bromides that hydrolyze slowly and are soluble in ethanol. That is, the chloride and bromide of magnesium and lithium, they are able to dissolve in ethanol and they hydrolyze slowly. The oxonium ions produced make the resultant solution acidic. That is it. The resemblance between beryllium and aluminium, that is the diagonal relationship or the chemical properties that are similar in these elements that make them behave the same. We say both elements are passive concentrated nitric acid. Both react with concentrated alkalis to form complex and mineral acids. That means these guys are amphotolic metals. They react with both alkalis and acids. When you get beryllium and you react it with a concentrated alkali, that is sodium hydroxide or potassium hydroxide, for us, our interest is a hydroxyl ion. Writing the ionic equation, you get beryllium salt plus hydroxyl ions plus water. You get beryllium tetrahydroxide or tetrahydroxoberylate ion plus hydrogen gas. If it is aluminium, you get tetraaluminate, tetrahydroxoaluminate. That is also the amphotolic or the complex that is formed when aluminium reacts with hydroxyl or concentrated alkalis and water plus hydrogen gas. With acids, these guys give us the corresponding salts of those acids, and also hydrogen gas is liberated. So you can get beryllium salt plus hydrogen ions aqueous. You get berylate, that is beryllium 2 plus ions in aqueous, and then you have hydrogen. So the salts that are formed by these guys, they are soluble. Both the elements form chlorides which are partly covalent and exist as dimers. Two ways, or it doubles. That is a dimer. Look at this diagram. It is more clear. This is the dimer of aluminium chloride. So both beryllium chloride and aluminium chloride, they give us a dimer. It does not exist as this one, this first diagram, where it is aluminium trichloride. It is dialuminium hexachloride. That is, you have two aluminium atoms plus 6 chloride atoms surrounding these two. So that is how it exists as a dimer. Their oxides are also amphotolic, as they are their hydroxides. That is, oxides. Look at the oxide of beryllium. That is beryllium dioxide. Reacts with the hydroxyl ions and water to give us a complex. So continuing, we are looking at beryllium oxide reacting with the hydroxyl to give us a complex of beryllium tetrahydroxide. Also, aluminium oxide, it gives us tetraaluminate or the aluminate ion. Likewise, with acids, it gives us the corresponding salts plus water. In this one on top, for beryllium oxide, there is a missing O on hydrogen. It is not hydrogen, it should be water. So here that means there is liberation of a water molecule. But if they were the corresponding elements, then they were so look at the hydroxides plus the hydroxyls. They also give us the berylate ions and the aluminate ions with concentrated alkalis, and with acids, they give us the corresponding salts, and water molecule is also released as a result. Their carbides also hydrolyze in water to form methane gas. You can look at the equations, that is beryllium carbide reacts with water to form beryllium hydroxide plus methane gas. You look at also the carbide of aluminium reacts with water to give us aluminium hydroxide plus methane gas. That is the chemistry of beryllium and aluminium. That is the diagonal relationship of beryllium and aluminium. So explanation as to why these guys, we already talked about them, why lithium, beryllium, lithium and magnesium show resemblance in the chemical properties. They possess similar electrode potentials, similar hydration energies, similar ionization energies, and their ions have similar charge densities and polarizing powers. That is the lesson for today. Thank you for watching. Kindly go to our YouTube channel and subscribe at Junior Jan Ndiamachi on YouTube. That is the name we use. And subscribe for more videos, and have a nice time.